Nunchaku is a cutting-edge quantization technology released by MIT Han Lab built on SVD Quant. It allows you to achieve nearly lossless image quality at faster speeds and with lower VRAM requirements. In the latest version, it is fully compatible with almost all components of the Flux ecosystem. The official team also plans to support 1.2.1, the best open-source video generation model on the market, in future versions. Excited? In this encyclopedia video, I'll provide you with a step-by-step tutorial that will guide you through the process of installing and configuring Nunchaku in Comfy UI. I'll also demonstrate the workflows to help you fully unlock its potential. First, I'll download a fresh portable version of Comfy UI from its official release page to show you how to install it step by step. Later, I'll demonstrate how to upgrade it within the V5 integration package that I've shared. After downloading and unzipping, the extracted folder looks like this. Now let's install the Comfy UI Nunchaku plugin provided by the Nunchaku team. Open the plugin's GitHub page and scroll down to the installation instructions. The prerequisite for installing the plugin is the Nunchaku library itself. Click on the provided instructions to jump to the new page. There are two ways to install it, but the source installation process is relatively complex and not suitable for most users. I recommend using the precompiled WHIL file. First, ensure that PyTorch version 2.5 or later is installed in your environment. Comfy UI will print the versions of components during startup, but we can also check it using pip at any time. Navigate to the Comfy UI folder, type cmd in the address bar to open the command prompt, and run this command to print out the PyTorch and Python versions. Currently, Comfy UI comes with PyTorch 2.7.1 plus CU128 and Python March 12, 10, so these versions meet the requirements. From the installation guide, you can find precompiled WHIL files on Hugging Face, ModelScope, or GitHub. Using Hugging Face as an example, the file names follow this structure. The number at the beginning, e.g. 0.20, represents the version number. Look for the latest version, such as 0.3.0. Next is the PyTorch version, in our case, 2.7. The CP part corresponds to the Python version, which is 3.12. Finally, choose your platform, Windows or Linux, so the file is the one we need. Click to download it. Once the download is complete, place it in the root directory of Comfy UI. Switch back to the command prompt and enter the command, python_embedded_python.exem pip install filename. Be mindful that the plus symbol in the filename may have been escaped as %2b. The installation completes quickly. You might see a few warnings about not registering the embedded environment scripts in the system path. These can be safely ignored. After installation, you can delete the WHIL file. Next, we need to install Comfy UI Manager. If you've already installed it, you can skip this step. Otherwise, go to its release page, download the compressed archive, and extract it into the custom_nodes directory. A simpler method is to use git clone, copy the provided command, open the command prompt in the custom_nodes directory of Comfy UI, paste the cloned address, and you're good to go. Returning to the Comfy UI root directory, you'll now see a newly added launcher. It supports fast FP16 accumulation mode, which provides better performance for GPUs in the RTX 30 series and newer. Double-click to launch Comfy UI. Click on Manager, search for Comfy UI Nunchaku in the plugin list, and install it. Once installation is complete, restart Comfy UI. If the interface looks like mine upon restart, then the Nunchaku plugin has been successfully installed. We'll demonstrate how to use it shortly. But first, let's talk about upgrading if you're already using an environment with an older version of Nunchaku, such as the V5 integration package that I've shared. Open the V5 integration package. Since it already contains many plugins and dependencies, I recommend backing up the python_embedded folder first for safety. Open the command prompt and use this command to uninstall the previously installed Nunchaku library. Make sure to confirm by typing Y. Cleaning up the old version is essential. Then, as demonstrated earlier, check the versions of PyTorch and Python. In my case, PyTorch is 2.6.0 plus CU126, and Python is 3.12.9. Use the same approach to find the appropriate WHIL file, download it to the Comfy UI folder, and install it using the pip command. Launch Comfy UI, use the manager to update the core Comfy UI application and the Comfy UI Nunchaku plugin. With these preparation steps completed, you're ready to go. Next comes the most critical step, downloading the models. The models required for Nunchaku are hosted in the official Hugging Face repository, including base generation models like Flux.1 Dev and Schnell, in painting models like Fill, ControlNet models like Depth and Canny, and the text encoder T5XXL. Among these, I find Dev, T5, and Fill the most practical. For ControlNet, I personally prefer using LoRa for simplicity. After selecting a model, you'll notice that each one comes in different formats, such as INT4 and FP4. Choosing the right one is straightforward. If you have a 50 series GPU, go with FP4. For others, select INT4. Models may come in different forms, some as a single .safetensors file, while others are in folder format. Single files are essentially the merged content of their respective folders. It's recommended to download the single file format whenever available. However, if the model you want only exists in folder form, you'll need to download the entire folder and merge it into a single file using the ComfyUI Nunchaku plugin. Note that the PyTorch version shouldn't be too low, otherwise, you'll encounter errors. Now, let me demonstrate how to use the Nunchaku plugin with the V5 integration package. After launching ComfyUI, click on the Workflow menu and then open Browse Templates. In the Custom Nodes section, you will find ComfyUI Nunchaku, which contains 14 different workflow templates provided by the plugin. I'll load the third row workflow, which uses the quantized version of the Flux.1 Dev model to generate images. The entire workflow setup is quite simple. The group of nodes in the middle of the interface is the same as the default Flux-based generation workflow. We just need to focus on the two model loading related nodes. First, let's look at the Flux model loading node, Nunchaku Flux DIT Loader. The model_path field currently supports both single file.safetensors and folders, though the official team plans to remove folder support after version 0.4. Therefore, it's better to use the merged single file format. You can refer to the earlier part of this video for guidance on downloading or manually merging models. My GPU is an RTX 4080, which belongs to the 40 series NVIDIA cards, so I'll select the INT4 version of the model. Users with 20 series and 30 series GPUs are also advised to choose the INT4 version. For users with 50 series GPUs, select the FP4 version. The cache_threshold parameter determines the caching strategy. First block cache. It caches partial computation results in order to boost inference speed while maintaining image quality as much as possible. For now, I'll set it to 0 to completely disable caching, and later I'll compare the effects of different settings. Under the attention implementation method, there are two options. Nunchaku FP16, this requires no additional installation, is fast, highly compatible, and supports most GPUs, including 20 series NVIDIA cards. It's suitable for most users. Flash Attention 2, this is optimized specifically for newer GPU architectures, 30 series and above, offering better memory efficiency, especially for large models or high-resolution tasks. However, installation is more complex and requires pre-configuring the Ninja and Triton environments. For Nunchaku models, Nunchaku FP16 already provides excellent speed and quality, making it the best choice for users who want a hassle-free setup. The image quality is virtually identical to that of Flash Attention 2. If you're not keen on environment configuration, stick to Nunchaku FP16, but if you're chasing extreme performance, you can try manually installing Flash Attention 2. The CPU_offload parameter determines whether a portion of the model's weights should be moved from GPU VRAM to system RAM, partly offloading computation to the CPU instead of relying fully on the GPU. The upside is that it reduces the risk of running out of VRAM, but at the cost of significantly slower performance. In simple terms, if your GPU has enough memory, disable this option to keep all computations on the GPU for maximum speed. If your VRAM is limited, you can enable it, which will be slower but functional. Alternatively, you can choose Auto. It will automatically enable offloading if your VRAM exceeds 14 GB. I have 16 GB of VRAM, but my recording software also takes up a portion, so here I'll enable CPU_offload. The device_ID parameter lets you specify which GPU to use. If you only have one GPU, it defaults to 0. The data_type parameter specifies the precision of the weights when loading the model. It's recommended to use Float16 if your card supports it. For cards like the 20 series, which don't support Float16, you can select Float16, though theoretically, it offers slightly lower performance. The I2F mode setting only applies to 20 series GPUs and controls the implementation mode for GEMM. You can ignore this option for other GPUs. Select the VAE from a local file. Next, let's check the text encoder loading node. The model type is Flux.1, and it loads both clip_L and the quantized version of T5_XXL. A major update in the V2 version of this node is that it no longer strictly enforces the sequence of T5_XXL and clip_L like the previous version did. The choice of quantization format, int4 versus FP4, follows the same rule as above. Select FP4 for 50 series GPUs, and int4 for non-50 series GPUs. For the T5_min_length parameter, which defines the minimum sequence length of T5 embeddings, it's recommended to leave it at its default value of 512. This value is higher than the hard-coded 256 in the dual CLIP loader node and can result in better image quality. For the prompt, I'll modify it to, a beautiful girl wearing a white dress. To ensure consistent comparisons, I'll set a fixed seed to one of my favorite numbers. I'll leave the other parameters unchanged and click Run. It takes 23 seconds to sample the image, though this is with CPU offloading enabled for the sake of recording. Normally, it would take only 8 seconds. Now, I'll adjust the workflow by replacing the Sampler Custom Advanced node with a simpler K-Sampler node. This removes many unnecessary nodes, simplifies the process, and makes it easier for me to test other features like LoRa, ControlNet, and PULID. I'll adjust the parameters to match the previous run and click Run again. The resulting image is nearly identical, proving that these two workflows are equivalent. This time, sampling took 20 seconds. Minor differences in runtime mainly depend on your system's current state. Next, let's adjust the cache threshold to the officially recommended value of 0.12 and run it again. The sampling time remains 20 seconds, and the output quality is nearly identical. On the surface, it seems like caching doesn't have much effect. However, as I mentioned earlier, performance testing requires multiple batches, diverse samples, and repeated trials with different parameters to draw convincing conclusions. In theory, enabling caching should provide speed benefits, so I encourage you to try it a few more times on your own to experience the potential improvement. Since I'll be primarily comparing image quality in the following tests, I will disable caching to avoid any interference. There has been ongoing discussion online claiming that the quantized version of T5 in Nunchaku affects the output quality. Today, let's directly compare different versions of the T5 model to see if that holds true. This loading node is actually compatible with standard T5 models. First, I'll replace the T5 model with the FP8 version, leaving all other parameters unchanged, and run it again. Very quickly, we've got a new image, and it looks almost identical to the previous one. Next, using the same workflow, I tested two more versions of T5, FP8_scaled and FP16. Comparing these four images side by side, I see very little difference in the actual results. So, if your GPU has limited performance, you can confidently use the quantized version of T5 without worrying about quality loss. Now, I'll switch to the default Flux model to see how long it takes to generate a base image. I'll add a model loading node, select the FP8 version of the Flux dev model, and replace the T5 in the text encoder with the FP8_scaled version. This is my go-to combination. Click Run. And the sampling takes 36 seconds in total, about 40% longer than Nunchaku's 20-second runtime. Comparing the generated images side by side, I think Nunchaku shows very minimal quality loss, making it an excellent choice for pure base image generation. Nunchaku can also work with turbo models, making it even faster. I'll switch back to Nunchaku's quantized Flux model and T5, and add a Nunchaku Flux LoRa loading node. I'll select the turbo LoRa model released by Alimama. Reduce the sampling steps from 20 to 8, and click Run. With more than half the steps eliminated, this sample only takes 10 seconds, and the output quality looks great to me. For turbo-type models, including the Schnell and Lightning series, if you encounter blurry outputs, you can try increasing the steps slightly, maybe to 12. In most cases, this will resolve the issue, and it's still much faster than the default 20 steps. Nunchaku doesn't just support turbo LoRa, it's compatible with almost all Flux LoRa models on the market. Here, I'll replace Turbo with a portrait LoRa that I often use. I'll restore the step count to 20. This LoRa doesn't require triggering keywords, so I'll run it directly again. The character's facial features are noticeably different, clearly demonstrating the effect of the LoRa. Flux Tools includes two ControlNet LoRa's, which can also be used in Nunchaku workflows. I'll select the depth LoRa and use this image loading node to input the image we just generated. Then, I'll process it into a depth map using the Depth Anything preprocessor from the all-in-one node. Next, I'll complete the rest of the ControlNet workflow. Since we now have control signals, I'll simplify the prompt to just a portrait of an animated style girl. Click Run. With ControlNet added, it's slightly slower, but we still get results in just over 20 seconds. The generated image follows the structure of the reference image closely. Flux Tools also includes large models with ControlNet functionality, and Nunchaku offers quantized versions as well. Here, I've also selected the depth model, disabled the LoRa node, and clicked Run. The output again followed the depth of the reference image. With the release of version 0.3.0, Nunchaku specifically highlighted its support for Union ControlNet 2.0, which is a consolidated model offering multiple control functions, including depth functionality. Let's give it a try. First, I'll switch the model back to the quantized version of Flux. This time, I'll use the standard ControlNet application node, Apply ControlNet. Combined with the ControlNet model loading node, I'll select depth using the Set Union ControlNet type node. Click Run. Oops! I forgot to connect the empty latent image node. Let me fix that and run it again. The depth effect here isn't great, it doesn't compare to the previous official version. However, I think this model's pose reference functionality is quite impressive. I'll switch both the preprocessor and the control type to OpenPose and click Run. This doesn't quite look right, probably because I had set the weight to 0.6 based on the depth test. For pose, I'll increase it to 0.8 and run it again. This time, the output matches the reference image's pose perfectly. PooLid is one of the few Face ID consistency solutions available in the Flux ecosystem, and Nunchaku also supports it. Here's how to use it. Delete some nodes we no longer need. Add the PooLid model loading and application nodes provided by Nunchaku, then connect everything properly. I'll continue using the previous image of the girl's face as a reference and adjust the prompt before clicking Run. Note that the PooLid model needs to be downloaded separately and placed in the models/PooLid directory. During runtime, the system will also automatically download the EVA Clip L14-336 model from Hugging Face, so make sure your internet connection is stable. The result is in. Comparing the two faces, they look quite similar. The FluxFill model allows for excellent in-painting and out-painting, and Nunchaku supports it as well. In the model loading node, select the quantized version of the fill model, add an in-painting node, in-paint model conditioning, and connect it properly. Disable any unnecessary nodes, paint a mask around the girl's neck, and save it. Add pearl necklace to the prompt, then click Run. The necklace fits in beautifully. Nunchaku also recommends using the Removal LoRa to remove content from images. Add a LoRa loading node and select the Removal LoRa. Let's switch to an image of a small robot dancing, paint the mask over the robot, clear the prompt, and click Run. The robot is gone. In its place, there are now a few flowers. However, the flowers clearly lack detail and refinement. This kind of issue is very easy to fix. We can run it again with Flux at a low in-painting strength. I'll add a Flux-based generation workflow and continue using Nunchaku's quantized model with an in-painting strength of 0.3. Click Run. And it's visibly much better. The Redux model for image referencing is also a commonly used one in the Flux Tools library. Let's try it with Nunchaku's quantized Flux model. This time, I'll save some time by adding Nunchaku's model loader node directly into the Redux workflow. I'll select the model and replace the original one before clicking Run. Redux is now active. The output clearly incorporates elements from the input image. I won't demonstrate further. Let me summarize. Nunchaku is like a supercharged accelerator for the Flux model series ***. It provides extreme speed, reduces VRAM requirements, and has almost no quality loss. It's compatible with LoRa, ControlNet, PuLID, and more, making it perfectly integrated into the Flux ecosystem. The only drawback is that installation is slightly more complicated compared to typical plugins, but I think it's absolutely worth it. I highly recommend giving it a try. Alright, that's all for today's video. All the models, plugins, and workflows featured in this video are linked in the description. Feel free to check them out if you're interested. See you next time.